This is one problem that even Harvard students struggle in. However, it is way simpler than you think. Well, when you analyze this integral, you see this is an exponential integrand, where the exponent is a quadratic. This is crazy, right? So how do we even solve this? Before we even try to tackle this, we need to see a possible root that this integral can bring us. So first we know that when we see a quadratic, there gotta be some completing of square. I think it's called completing the square. And you notice that whenever there's an integral in the bounds negative infinity to infinity, and it's usually e to some number, some constant, you know this has to do something with Gaussian integrals, right? Gaussian integrals. So we can tell ourselves that this integral will eventually lead us to some possible result of the Gaussian integral. Okay, so what is the Gaussian integral? Okay, I'm just going to give you a very, very generalized formula for the Gaussian integral. But don't get scared. I'm pretty sure many of you know a lot of standard results with respect to Gaussian integration, right? So the result is infinity, 0 to infinity, x to the p e negative q x to the r dx is 1 over r q to the power of p plus 1 over r n times gamma of p plus 1 over r. This is a handful. And no, I am not gonna even tell you to memorize this formula. We know something called the Gaussian integral. There are a lot of general formulas that we know, and one of them is our favorite. The integral of negative infinity to infinity of x to the negative ax squared is just known as square root of pi over a. This is a very famous Gaussian integral. I think that's all we need today, right? Can't be more complicated than we think. Okay, now let's start solving this. First, let's complete the square, right? This is a typical completion of square that all of us learn in primary school, right? This is just e to the negative 5 x minus 2 over 5 squared minus 4 over 25. Sorry. Which is the same thing as e to the negative 5 x minus 2 over 5 squared plus 4 over 5 minus 1, right? And now you notice that e to the negative 1 over 5, and when you simplify this, there's just negative e to the negative 1 over 5. We can just, well, factor it out because, well, it's a constant. This is a constant. So we can factor out e to the negative 1 over 5, an integral of negative infinity to infinity of e to the negative 5 over x minus 2 over 5 squared dx. So now this stage is where Harvard students struggle in. How do we even proceed? Okay, now we can relate this to our favorite Gaussian integral. How do we, well, transverse that? Okay, what do you notice? We notice that there is negative ax squared. We also want negative 5. We want x squared here, but it's x minus 2 over 5. So we need a clever substitution. So now I'm going to do a substitution that you probably never dreamt of. But it's actually quite intuitive. We're going to do y equal to square root 5 over x minus 2 over 5. What good does this do? Okay, now let's not jump the gun. Let's first find dy, which is what? 1 over square root 5 times dy. Sorry, dx. mind. It's dx times dy, right? Because we bring it over. So now how does this proceed forward? So now what we do is we notice that when we substitute this into here, we can factor out the negative or 1 over square root phi as a constant. So it's still e to the negative 1 over 5, 1 over square root 5. Then let's continue with integral. Integral of negative infinity to infinity. What do you notice? This entire thing is just e to the negative y squared. Isn't that awesome? We just collapsed this very stupidly looking integral into our favorite Gaussian integral, which is just the exact same thing as e to the negative 1 over 5, 1 over square root 5, and we just apply the Gaussian integral. Well, in this case, a is non-existent, so we end up with this. And when we combine them, we get e to the negative 1 over 5 over square root of pi over 5. This is our answer. So this seemingly, well, it looks simple to the naked eye, but it's actually way more harder than you think. But when it comes to a Harvard student, you're like, how do I even proceed forward? And yes, we just apply the Gaussian integral. Well, it's not really, you won't really call it hidden. And I'm sorry, I think I made a mistake. It's actually e to the negative a over x squared. I think that's a bit confusion I made, but let's get it clear. Right? Make sense? Thank you guys.